All right, I'm here with Sam Kuypers. Sam, thanks for being here.
Yeah, thanks for having me on.
No problem. So you've been working on an alternative to quantum field theory, and it seems that constructor theory might help you with your research. But before we get into any of that, what is quantum field theory in broad strokes?
Yeah, so I thought I would explain quantum field theory through classical field theory. And in classical field theory, a classical field is a physical system that has observables at each point in space. So an example of this is a, a temperature field. So if you consider the temperature in a room, then effectively you have a temperature field because there's a temperature that you can associate with every point in that room. And what makes it a classical field is that the temperature everywhere in the room has a sharp value. So more generally, a classical field would be anything with observables at points in space with sharp values. And quantum field theory, on the other hand, has, just like classical field theory has observables at each point in space, but these observables are not necessarily sharp. So the state of the observables is uncertain. It could be that it's in a superposition of multiple values at the same time. And I think we want to talk about the properties of this field more, and I can do that now. I can explain some of the algebraic properties of such a field. Because for a field to have unsharp values, it needs to have observables at a particular point in space, a set of observables at a point in space that don't commute with one another, which means that which in practice means that if you were to observe one of the field's observables at that point in space and then another one, the outcome of the experiment would be different if you measured it the other way around. If you first measured A and B, it would be a different result from first measuring B and then A. And algebraically, it means that the multiplication of these variables, of these observables, is not the same, that the order of multiplication of the variables matters. And so in very broad strokes, so to summarize, a quantum field is a physical system that has observables at each point in space, and these observables they have some non-commutative properties such that they can be unsharp, unlike classical fields, which are necessarily sharp.
So what are the problems that arise in this conventional way of expressing quantum field theory, and what is it about the conventional formulation of quantum field theory that causes these problems in the first place?
Yeah, so I think there are several problems, and maybe the most prominent one is that these quantum fields have so-called divergencies. So there are observables of the field which whose expectation value goes up to infinity, basically. And that's unphysical, it's an unphysical result. And the way people deal with that, or I should say, I think it's now commonly accepted that the reason for these divergencies is that the interactions of a quantum field at very small scales are very violent. And the solution, therefore, is to basically do quantum field theory while you neglect the interactions at very small distances, and therefore you get kind of an effective field theory approach. So you have a field theory where you, say, cut out the fine structure, or the structure at very small scales, and you do so by having an effective field theory, which is basically saying you can pretend that this structure isn't there, and then still get results through a thing called renormalization. And I think that's now the common way in which people, this is the way in which people deal with these divergencies. But it's also a problem in the sense that it means that your theory isn't universally valid. So at very small scales, people agree that quantum field theory can't be valid, and that the theory tells us this because it needs renormalization. But so there needs to be another theory, a universal theory that holds at these, that will explain the interactions at very small length scales. And so that's one problem, and I think that's quite a big problem. The other problem is that the fields can carry too much information in them. So we know from general relativity that there is a limit on the amount of information that can be stored in a finite region of space-time. And basically, the limit is the amount of information you can store into a black hole, such that if you store too much information in a finite region of space, then you automatically turn that region into a black hole. And quantum field theory, on the other hand, seems to suggest that there is no bound on the amount of information you can store in a finite region of space. And the reason for that is, again, to do with this commutativity between observables. Namely, the field observables of a quantum field at different points in space necessarily commute with one another. And observables that commute can be independently prepared and measured, meaning that you can store information in them separately. Now, since the field observables at different points in space commute with one another, you can independently prepare and measure them, and thus store information in them. And there are infinitely many of these commuting observables in a finite region of space. So it seems to suggest that you can store an arbitrary amount of information in such a region. And that contradicts this notion from general relativity, the Bekenstein bound, that you cannot do that. You can only store a finite amount of information in the field. So that is another problem, which I think exists within what I would call orthodox quantum field theory.
So if I'm understanding correctly, the two, or at least two of the problems with orthodox quantum field theory, one is that at fine enough scales, it leads to unphysical quantities such as infinite expectation values. And then another is really a conflict between theories, namely the expectations of how you can store information in orthodox quantum field theory contradicts what general relativity says is possible with respect to information. Is that right?
Yes, and I think these problems are related. Also, I should say, people nowadays would disagree with you that the infinities are a problem because they have these renormalization schemes. The trade-off is that they can deal with the infinities, but they have to give up being able to provide a description of the field at very small length scales. So they basically have to cut those out. But it's a trade-off that people are willing to make. So I think there might be disagreement about whether or not the infinities themselves are still the issue. But they definitely cause other problems, even if you try to solve them. And as for the relation between the divergences and the infinite amount of information in the fields, so this idea that the field observables at different points in space commute with one another is actually a standard assumption in quantum theory in general. It's namely the assumption that, it's called the canonical commutation relation. And what it says is that different systems, so different physical systems, have to have observables that commute with one another such that you can independently treat and measure them and interact with them. And in the field theory case, what happens is that this canonical commutation relation, this idea that the fields observables at different points in space commute with one another, actually introduces a divergence. So if you consider the field observables at two different points in space and then slowly bring them together, what you'll find is that it's 0, 0, 0 as long as the fields are at distinct points, but the field observables at the same point in space blow up to infinity. So this, for the technical term, would be there is a direct delta function in the commutation relation, and that causes the fields to blow up. And actually, I think there's also even a kind of connection with the problems that existed in classical field theory and quantum field theory, which is that there's this basically classical fields used to be problematic because they had these infinite degrees of freedom, which is maybe a discussion we can get into later. But in a way, it's the fact that these fields have too many information degrees of freedom. So this degrees of freedom, there's infinitely many degrees of freedom which we can store information in these fields. And I think there's a parallel between the problems that exist in classical physics and the problems that exist in quantum physics now. In many ways, field theory has always been problematic, but deeply fundamental. So it's a nice area of physics.
So if this canonical commutation relation, as you called it, causes these problems to emerge in orthodox quantum field theory, why was it accepted in the first place?
I think it has to do with the fact that people wanted quantum theory to be local. So different physical systems have their own algebra, but they always have imposed on them that no matter their specific algebra, the algebra of the larger system, of the composite system, is such that the algebra of the subsystems commutes with one another. So if you have an observable of one of the subsystems, that observable always commutes with an observable from the other system. And that basically ensures in quantum theory that if you do anything to a subsystem, you can independently prepare and measure that subsystem without affecting the other systems that might exist as well. And these kind of considerations about locality, local realism even, and non-signaling were the reason why the canonical commutation relations were required in the first place. So meddling with those seems to be very tricky, or I think people would be scared of breaking the no signaling rules, for example, or of violating locality or something like that if you were to change the canonical commutation relation.
So have any solutions been proposed to resolve some of these problems in conventional or orthodox quantum field theory?
Yes, so David Deutsch in 2004, I think, published a paper, or put a paper on the archive, I should say, about an alternative quantum theory, quantum field theory, called qubit field theory. And the assumption of qubit field theory is that there are physical systems at each point in space, or rather at each event in space-time, which do not necessarily obey the canonical commutation relation. So if you evaluate the field at two very nearby points in space, the observables of those points in space will not necessarily commute with one another, which violates the canonical commutation relation. And I think it's a very nicely symmetric approach to quantum field theory. For one thing, because these commutation relations that are imposed on the field observables in the usual quantum field theory are asymmetric with respect to time. So field observables at nearby points in time are never assumed to commute with one another. And they are assumed to commute when they're at different points in space. And this is one of the things that qubit field theory gives up, and basically it symmetrizes the way we treat space and time in quantum field theory. So different points, so observables at different points in time don't necessarily commute, and similarly in qubit field theory, different points in space, or observables at different points in space, also don't necessarily commute. And I should also add one of the nice things about qubit fields is that they are everywhere finite. So they're the state space, if you want, is finite dimensional, and there's no divergency. So there's nothing in the theory blows up to infinity. And I think that is one of the nicest things about the theory. I mean, I think there's many things to enjoy about qubit field theory, but it's nice that they are very well behaved compared to orthodox fields.
And so qubit field theory drops the canonical commutation relation, and it solves the existence of infinities that plagued orthodox quantum field theory. Now, you had said that one of the reasons the canonical commutation relation was accepted in the first place in orthodox quantum field theory was so that the theory was local. Is qubit field theory local?
Yes, it's very interesting. So the qubit fields have local equations of motion, meaning that the equations of motion of a field only depend on the field at a particular point and finitely many of its spatial derivatives. So this nice, it's almost like a loophole that allows the theory to still be local without it adhering to all these canonical commutation relations that are usually necessary within quantum theory to ensure that a field behaves locally. So yeah, quantum field theory is able to preserve one of these important properties that I think we should want physical systems to obey to. It's one of these principles that we should require of our theories. Locality is a thing that qubit field theory also obeys.
Now, how would constructor theory help to advance a theory like qubit field theory?
Yeah, so one of the reasons why qubit field theory was proposed is to find out about alternative quantum theories that maybe have a limited information carrying capacity, meaning that the amount of information you could store in such a field in a finite region would be limited. But at the moment, there is no theory of measurement for a qubit field. And the reason why there isn't is because this commutation, the canonical commutation relation in quantum theory, is deeply connected to information and determining what the information carrying degrees of freedom of your field are. And by altering that in qubit field theory, you basically have to derive a fully new theory of measurement in order to determine what the information variables of the field really are. And I think the way in which constructor theory helps with that problem is that constructor theory provides a theory-independent way of thinking about measurements. So constructor theory is like a meta theory of physics, which tells us, given a particular theory, what the theory should adhere to for it to have things like information and measurable quantities, etc. And I think that really streamlines the problem solving for this particular issue, because we now don't, instead of having to think from the grounds up what a measurement could mean for a new theory of physics like qubit field theory, you can instead immediately say, well, there's this general framework that constructor theory provides, and we just have to fit our theory within that general framework, which is still an open problem, but it's much simpler than having to think about the problem of what a measurement really is before you even get to solving it. So in a way, we can skip a step.
So what is it about constructor theory, or in this case, the constructor theory of information in particular, that makes it easier to determine what will constitute a measurement in qubit field theory?
Yes, so the constructor theory of information, as I understand it, provides us with a definition of information, which is it's an attribute of the system that can be used to perform classical computations with, and which can be copied given a suitable substrate. And those will be the information variables. So that will be information in that theory. And using that definition, we can kind of extract from qubit field theory what it is within that theory that is information. So it's like using this meta theory of physics to get to the answer quicker, because we already have an understanding of what measurement is in general. That is no longer a problem that we have to think about. So we can now solve this problem quicker because we can skip that step of having to think about what measurements really are. Because again, we already know that.
And I wonder if you could give us a brief example of what making a measurement looks like in orthodox quantum field theory now.
I think I can kind of like give a sketch of what that means. So if you, maybe a broader example would be, if you have two physical systems, two quantum systems, then because they commute with one another, you can measure the observables of one of the systems without affecting the observables of the other system. And but you can't measure the observables of the same system without affecting those. So if you have a single qubit, for example, then a qubit has three observables, the qubit descriptors, and you can measure one of them. But if you subsequently measure another one, then your previous measurement result will have affected the second measurement, and vice versa. So this is what the non-commutativity means. It means that if you measure A and then B, it's not the same as measuring B and then A. And this basically, you treat the field observables of a quantum field like separate physical systems. They each have two observables each, and measuring those and interacting with those can be done independently from the other field observables. In practice, it will always be to a rough approximation, but the theory gives no bounds to how well you can independently interact with one part of that field. And it's because you're dropping the assumption in qubit field theory that interacting with the observables of 2 points of at 2 different points in space is like affects the measurements of those observables. So it seems like if you were to observe first the system A, or first the field at point A and then the field at point B, they would affect one another because the field observables don't commute with one another. And they're, in a sense, it's like they are kind of part of the same physical system, which is not the case in orthodox quantum theory. And this is very strange. It's unusual within the orthodox approach. I don't think there is currently a way, or there's no current solution to that problem. We don't yet know what that means for the information in the qubit field. And yeah, so that's a very brief overview of how this notion of measurement in quantum field theory is not carried over to the notion of a measurement in a qubit field, which again is because the commutation relation, the canonical commutation relation, is very important for defining information in orthodox field theory, and you simply drop it. So you have this new problem to solve. And again, I think that's where constructor theory will come in and be very useful.
It almost sounds like qubit field theory, if it's shown to be correct or have fewer errors than orthodox quantum field theory, then the world is even more quantum than we had previously suspected.
Yes, but I put it like that at some point as well. At least that's how I think about it. Like the property that things commute is a very classical property. We're very used to being able to interact with things that commute, the measurements of which commute, and in fact, non-commutativity is a purely quantum mechanical phenomena. It's maybe not purely quantum mechanical phenomena, but it's a very characteristic property of quantum systems, and yet we've treated the combining of quantum systems rather classically in a way, because we've introduced on assumption the idea that the observables of separate quantum systems must commute with one another. And yeah, so I agree with you that if you drop that assumption, then things will become even more quantum mechanical. You have even more of these observables that don't commute with one another, and it's adding another layer of strangeness to your description of reality.
So what open problems in other areas of quantum physics or quantum mechanics do you think researchers could help to solve by also dropping the canonical commutation relation, as David Deutsch has done in qubit field theory?
I think if qubit field theory turns out to be true, then it will just be the theory of quantum fields. But of course, there's many tests that it would have to go through. So, for example, before it can really stand up as a theory, I think it should solve this problem of information, which was one of the reasons for its invention, which again, constructor theory will be very vital to. But there's other problems like how the field should interact with other fields, And yeah, there are other problems that the qubit field theory should solve. But if it manages to solve those, then I think it will be a reformulation of field theory as we currently know it. Then, for example, if quantum field theory is true, that means that there are no fields that adhere to the canonical commutation relation, because commutativity can spread to other theories, to other fields when it interacts with those fields, meaning that there's really no such thing as a commuting field, or as a field that adheres to the canonical commutation relation. That means that you have to reformulate all of quantum field theory in terms of qubit field theory, which will then mean that you have to, for example, solve the standard model, or give a description of the standard model, not with orthodox quantum fields, with these qubit fields. And that would be a very exciting project. Like if qubit field theory takes off, then that would definitely be one of the things it would be applied to. And yes, I think in general there should just be a research project about non-commutativity. Another area in which it shows up, for example, is fields in a black hole, I think. So the quantum fields inside a black hole cannot adhere to the canonical commutation relations either. And it would just be exciting stuff. Maybe there will be, secrets to gravity will be, I think there will be a link to general relativity possibly. And that is also very exciting. Like what would qubit fields tell us about the relationship between quantum mechanics and general relativity? Open problem, but a very exciting one.
Yes, those all sound like very exciting areas of research. It's interesting to me that this non-commutativity is not really emphasized, at least sort of in the popular science areas that lay people consume. You don't hear much about this as a potential pathway to, let's say, understanding the relationship between general relativity and quantum mechanics. You hear much more about things like string theory and loop quantum gravity and so forth.
Yes. One reason would be it's a very tentative solution, and qubit field theory is in its infancy at the moment. And so it's somewhat unsurprising that people haven't noticed this more, but I think at the same time, more and more people are noticing problems with quantum field theory, which have a similar flavor. So for example, Sean Carroll wrote a paper a while back about why the state space of any physical system should be finite, including for quantum fields, which is a very related problem. So I don't think he concluded anything about how quantum field theory should change. But in this paper, he noted that, there is definitely a problem with the size of the state space of a quantum field at the moment, which he wanted to solve. And again, that's related to this issue of how much information you can store in a field, which was something he also noted. I think he phrased it in terms of entropy. But yeah, so that is another researcher like seeing the same issue. And I think if qubit field theory were to make progress, it would appeal to many people's intuitions about how space-time and how quantum fields should work.
Well, this has all been very exciting, Sam. So thank you very much for your time.
Cool. Yeah, no problem. Thanks for having me again. It's been great.
Yep. Take care.
Cool. Yeah. Take care. Bye-bye.
Bye.